members, to help you prepare for your GCSEs, we're doing a few practice problems for you so you can see how we work through them. Today I've picked a foundation level physics exam question, and I'm going to talk you through how we go about solving this question as well as the content of the question. The question is a question about sound produced from an air horn in a lorry. So imagine a lorry driving by and it's blaring its air horn, so you can imagine that in a real life situation. This question, it has multiple parts. A lot of the exam questions will have multiple parts, and the best way to approach these kind of questions is to read through all the parts initially. So on the board I've written all the parts of the problem. The first section just says, use one word to complete the following sentence. Sound waves cause air particles to blank. So you can think of lots of concepts about sound and what you've already learned about sound in your classes. One of the things they're looking for here is specific movements about air particles. So to say the air particles are moving isn't specific enough for the context of the problem. What they're looking for here is for you to say the air particles are oscillating or vibrating due to the sound waves moving through them. So I've just written the word oscillate to complete the sentence. That part of the problem is now done. The second part of the problem requires a bit of calculation. It gives you the frequency of the air horn, which is a constant frequency of 420 hertz. To remember what hertz are a specific unit for frequency, and it's a per second, so it's 1 over a second. It also tells us that the wavelength of the sound waves is 0.8 meters. And then it asks us to calculate the speed of the sound waves. This equation should be given to you on the equation sheet that's included with the exam. So if you don't remember it, that's fine, just make sure that you refer to your equation sheet on the exam. The equation that you need to calculate the speed of a sound wave is just frequency multiplied by the wavelength. So the equation looks like this. We've got speed, which I'm representing by V, equals frequency, which I represent by a fancy F, and I multiply that by lambda. Lambda, which is often used as the expression for wavelength. In this case, we're given the frequency as 420 hertz and the wavelength as 0.8 meters. So those are the two numbers I need to plug into this equation to get my answer. I've already done the math, and I can tell you that 420 times 0.8 is 336, and the units are going to be meters. Remember I said hertz was a 1 over second, so the units are going to be meters per second, which is what you would expect for a quantity of speed. So that part is now done. The third part of this equation says a person is standing at the side of the road. As the lorry goes past, they hear the sound from the air horn change pitch. And then the question asks, what determines the pitch of the sound? And it gives you three options: the amplitude, the frequency, or the loudness. Now this is something you're going to have to remember about the concepts of sound that you've learned in your course already. Remember, the amplitude of the wave is simply just how big it is. The frequency of the wave is how often it goes through a certain point. And the loudness of the wave is just the decibel level of that wave. In this situation, pitch is determined by frequency. And that is just a definition that's given with sound. So that's something you're going to need to remember from your lessons, and make sure you revise and understand the different parts of a sound wave and what those parts mean for the sound. There's two more parts to this problem. The fourth part is, as the lorry moves away from the person, the air horn continues to produce the sound waves with that same wavelength of 0.8 meters that we used in the second part. Then the question asks, what is the wavelength of the sound the person heard? And again, you're given options. It's either shorter than 0.8 meters, equal to 0.8 meters, or longer than 0.8 meters. So, again, you have to think about what the problem is asking. It tells you that the lorry is moving away from the person. So the lorry is travelling away. Imagine yourself in this situation when an ambulance goes by or something making noise drives past you. How does that sound change? And remember our previous part of the question where we talked about pitch. Now, as that pitch changes, because it's coming from a moving object, that would indicate that the wavelength is going to change from the person perceiving the sound. So even though the sound itself is being produced at a constant wavelength, the person on the side of the road is going to hear a wavelength that is longer than 0.8 meters because the lorry is moving away from him or her. If the lorry were moving towards him, he would hear a higher frequency, which would indicate to him that the wavelength is actually shorter. If the person were standing by the lorry and the lorry were not moving at all, he would hear a wavelength that would be equal to, because there wouldn't be any movement involved with the sound. The final part of the problem asks us to consider that previous part, so all the parts are kind of building on each other. It says the sound waves the person hears from the moving air horn are different to the sound waves the air horn has produced, which I've just discussed a little bit. This is actually a specific effect that's given in physics, and it's asking what is the name given to this effect. So what is the name given to the perceived change in wavelength of the sounds produced by a moving object? We've got three options here. It's given us diffraction, Doppler, or refraction. Now the answer here is the Doppler effect, which is something that you should have heard about in your lessons. If you're unsure, think about the other options. Both diffraction and refraction, in dealing with wave mechanics, either light or sound, deal with that wave travelling through a different medium. Because the sound wave is still travelling through air to the person hearing the sound, neither diffraction or refraction is a suitable answer in this case, because there's no different mediums that the sound is actually travelling through.